The Milky Way is far more than the pale mist we see stretching across the night sky. It is a vast, gravitationally bound island of stars, an enormous bar-shaped spiral galaxy classified as type SBBC, meaning it possesses a pronounced central bar and moderately wound spiral arms. From our position buried deep within its disk, we cannot see its full structure directly, but decades of radio, infrared, and stellar mapping missions have revealed its true form: a rotating, star-filled metropolis with intricate arms, a glowing bulge, and a halo that extends far beyond what our eyes can perceive. Astronomers place the formation of the Milky Way at around 13.6 billion years ago, making it nearly as old as the universe itself. Its earliest stars were born shortly after the first galaxies condensed from primordial gas. Since then, the Milky Way has grown through steady star formation, accretion of interstellar gas, and repeated mergers with smaller galaxies, each event adding layers to its structure and complexity. Today, the Milky Way stands as a dominant member of the local group, the small cluster of galaxies our cosmic neighborhood belongs to. Alongside Andromeda and the Triangulum Galaxy, it forms a gravitational triangle that shapes the motion of dozens of smaller satellite galaxies orbiting around them. But among all these systems, the Milky Way is the one we call home, the only place in the observable universe where we know life has taken root. We live inside one of its spiral arms, but the galaxy itself is a colossal structure spanning nearly 200,000 light-years from edge to edge. Its central bar channels gas toward the core, feeding a long history of star formation. Its arms curl outward like luminous rivers, each one filled with billions of stars at every stage of life. Dust lanes weave between them like dark threads, hiding and revealing different layers of the galaxy's anatomy depending on the wavelength of light we observe. To understand the Milky Way is to understand our origins. Every atom in our bodies, carbon, iron, oxygen, was forged inside ancient stars that lived and died in this galaxy long before the sun was born. Every cycle of creation and destruction leaves a chemical imprint on its stars, its gas, and even on us. The Milky Way is not just the place we inhabit. It is the ancestral environment that shaped our chemistry, our planet, and every form of life on Earth. When we look toward the band of light arching across the sky, we are seeing just the thinnest slice of a vast, ancient system, a galactic home whose true scale, beauty, and history extend far beyond the horizon of what human eyes can grasp. From inside the Milky Way, we are like people trying to understand a forest while standing under its densest canopy. We do not see the clean, elegant spiral a camera outside the galaxy would reveal. Instead, we see a bright, crowded band of stars cutting across the sky, crossed by dark, irregular gaps. Those dark lanes are not empty space, but enormous clouds of interstellar dust and gas that absorb and scatter visible light. This dust forms a thick, uneven veil along the plane of the disk, especially toward the galactic center, blocking our direct view of the inner structure. When we point optical telescopes toward the middle of the galaxy, the light from distant stars is dimmed, reddened, or completely hidden, so the true arrangement of arms, bar, and bulge remains partly concealed. To peek through this veil, astronomers rely on infrared observatories such as Spitzer and WISE. Infrared light can pass through dust much more easily than visible light, so in these wavelengths the Milky Way looks dramatically different. Regions that seem dark and empty in optical images suddenly fill with stars, filaments, and hidden structures. Spitzer has mapped the inner disk and bar, revealing how the stars trace a long central bar and loosely wound spiral arms, while WISE has surveyed the full sky in infrared, giving us a more complete census of stars across the galaxy. Even with these tools, reconstructing the Milky Way's overall shape is extremely difficult, because we are trapped inside the disk, about 26,000 light-years from the center. We cannot simply step back and take a full portrait. Instead, we must infer the structure from partial, line-of-sight measurements. Distances to stars and gas clouds carry uncertainties. Dust affects brightness and color in ways that must be corrected. Different traces, young stars, old stars, gas, dust, do not always align perfectly. Radio maps of hydrogen, infrared maps of stars, and surveys of star-forming regions all give slightly different clues. Astronomers then combine these data sets into complex models, like reconstructing the shape of a city from thousands of street-level photos taken in fog. This is why there is still debate about the exact number and shape of the spiral arms, or the detailed thickness of the disk. We know the Milky Way is a barred spiral galaxy, and we understand its broad structure, but every refinement requires careful work against the limitations imposed by our dusty, embedded point of view. The Milky Way is not a uniform structure but a layered, interconnected system made of several major components, each with its own role in the galaxy's evolution. The disk is the broad, flattened region where most of the stars, gas, and dust reside. It contains both young and middle-aged stars, along with enormous molecular clouds that serve as nurseries for new stellar generations. Threaded through this disk is the bar, a long, elongated structure of densely packed stars at the galaxy's center. The bar acts like a gravitational engine, funneling gas toward the inner regions and shaping the motion of stars throughout the galaxy. Extending outward from the bar are the spiral arms, sweeping arcs rich in star-forming regions. These arms are not rigid structures but density waves, areas where gas clouds are compressed, triggering bursts of stellar birth. Closer to the core sits the bulge, or central ball of stars, made mostly of older stellar populations with little active star formation. Surrounding the entire galaxy is the halo, an enormous spherical region containing ancient stars, globular clusters, and a vast amount of dark matter that provides most of the galaxy's mass. At the very heart of the Milky Way lies Sagittarius A*, a supermassive black hole with about 4 million times the mass of the Sun. Though invisible directly, its presence is known from the rapid orbits of nearby stars, which move at extreme speeds under its gravitational influence. Together, these components form a dynamic, evolving system, a galaxy shaped by billions of years of rotation, mergers, star birth, and star death, all woven into a single cosmic structure. The Milky Way is far larger than the glowing band we see across the night sky, and even larger than astronomers once believed. Its true diameter is now estimated to lie between 170,000 and 200,000 light-years, a range that reflects both the precision of modern measurements and the complexity of defining where a galaxy truly ends. Earlier generations of astronomers believed the Milky Way spanned roughly 100,000 light-years, but more recent surveys, especially those using infrared observations, hydrogen line radio mapping, and Gaia's stellar motion data, have revealed that the galaxy stretches much farther. The outer disk is not a clean edge but a warped, extended structure with faint stars, gas, and streams stretching deep into space. Some of these outer regions were once too dim to detect, hidden behind dust or simply too sparse for older instruments to notice. Now, with improved sensitivity, we can see that the stellar disk merges into a low-density outskirts that continues much farther than expected. In addition, the Milky Way's gas envelope extends even farther than its stars, and the halo of dark matter that binds the galaxy extends for hundreds of thousands of light-years beyond that. But when we speak about the diameter of the visible stellar disk, the most widely accepted scientific range is 170 to 200,000 light-years. This makes the Milky Way one of the larger barred spiral galaxies in the nearby universe, large enough to contain hundreds of billions of stars and enormous regions of gas and dust, yet still small compared to giant ellipticals that span over 1 million light-years. Understanding its diameter gives us a sense of scale. When light needs hundreds of thousands of years just to cross the galaxy, we begin to grasp how vast our cosmic home truly is. The Milky Way is often imagined as a thin, flat disk, but in reality its vertical structure is layered and complex. The thin disk, where most of the galaxy's young and middle-aged stars reside, has an average thickness of about 1,000 light-years. This region contains the majority of the gas, dust, and star-forming clouds, and it is where the spiral arms are most clearly defined. Because it holds the densest concentration of material, the thin disk is the part of the galaxy most visible in optical light, forming the bright band we see across the sky. Yet above and below this layer lies a second, more extended component, the thick disk, a population of older stars that stretches roughly 3,000 to 6,000 light-years in height. The stars in the thick disk are typically older, more metal-poor, and move with different orbital patterns than those in the thin disk, suggesting a different formation history, possibly shaped by early mergers or by heating of the youthful galactic disk billions of years ago. This thicker layer contains far fewer gas clouds and little ongoing star formation, giving it a smoother, more diffuse appearance. Together, these two layers form a vertically stratified structure, a bright, dense, star-forming sheet sandwiched between older, puffier stellar populations. When we observe the Milky Way edge-on in external galaxies like Andromeda or NGC 891, we see similar double-layered disks, confirming that this vertical architecture is a common feature of large spiral galaxies. Understanding the thickness of each component helps astronomers trace the galaxy's evolutionary history and decode the processes that shaped its formation. The Milky Way is a vast stellar metropolis, and although we cannot count every single star directly, astronomers can estimate its population using measurements of mass, luminosity, and star density. The best factual range we have today places the number of stars in our galaxy at roughly 100 to 400 billion. This wide interval is not a sign of uncertainty in astronomy, but rather a natural consequence of how varied stars can be. Many stars are small, faint red dwarfs, so dim that even in our own neighborhood they can remain hard to detect. Others are hidden behind dense clouds of dust, or lie far across the galactic disk where extinction makes them nearly invisible in optical wavelengths. Infrared surveys, like those from Spitzer and WISE, greatly improve our ability to detect faint stars, but even these telescopes cannot completely penetrate every dusty region or resolve every star in the crowded inner disk. Instead, astronomers calculate the galaxy's total stellar mass and compare it to the typical mass distribution of stars to estimate the population. When all this information is combined, the result is a statistically supported range, hundreds of billions of stars, each with its own path around the galactic center, its own age, composition, and potential planetary system. In this sense, the Milky Way is not just a galaxy, it is a collection of stellar worlds on a scale nearly impossible to fully grasp. Every point of light in the night sky is just a tiny fraction of this enormous, luminous population. The Milky Way's mass is far larger than what we can see directly. When astronomers speak about the galaxy's mass, they distinguish between baryonic mass, the normal matter made of atoms, and the total mass, which includes the invisible contribution from dark matter. The baryonic component consists of stars of all types, interstellar gas in both cold and hot phases, and vast clouds of dust that thread through the spiral arms. Altogether, this visible and detectable matter accounts for only a small fraction of the Milky Way's true weight, roughly 60 to 100 billion solar masses, depending on the exact distribution of gas and the inferred number of faint, low-mass stars. But when astronomers measure how fast stars orbit the galactic center, especially far from the core where visible matter becomes thin, the rotation speeds stay unexpectedly high. According to the laws of gravity, this is only possible if the galaxy contains far more mass than what is seen. These motions reveal an enormous dark matter halo encapsulating the Milky Way and extending hundreds of thousands of light-years beyond the visible disk. This halo shapes the galaxy's gravitational field, governs how stars move, and influences how satellites orbit. When all contributions are added together, baryonic matter plus dark matter, the Milky Way's total mass is estimated to lie in the range of 1 to 1.6 trillion solar masses. Although dark matter cannot be observed directly, its gravitational effects are measured with high precision, making this mass range one of the most robust large-scale properties of our galaxy. The result is a picture of a galaxy whose luminous part is only the thin surface of a far more massive, invisible structure. The solar system occupies a position neither too close to the violent galactic center nor too far into the sparse outskirts. We orbit the Milky Way at an approximate distance of 27,000 light-years from the galactic nucleus, comfortably situated within the Orion Arm, a minor spiral structure between the larger Sagittarius and Perseus arms. This radial distance places us in what astronomers sometimes call the galactic habitable zone, not because it guarantees life, but because the environmental conditions are comparatively stable. Closer to the center, stars are densely packed, supernova rates are higher, and the gravitational environment is turbulent due to the presence of the central supermassive black hole, Sagittarius A star. Farther out in the halo, heavy elements are scarce, making it harder for complex planetary systems to form. Our orbit at ~27000 light-years strikes a balance. The stellar density is moderate, the radiation environment is relatively gentle, and the presence of heavier elements, produced by earlier generations of stars, supports the formation of rocky planets like Earth. This position also determines how we move. The entire solar system orbits the galaxy at roughly 220 to 240 km is, completing one full revolution, sometimes called a galactic year, in around 230 million years. While we travel, the stars around us shift slowly, spiral arms drift, and the Milky Way's shape continues evolving. Yet our distance from the center remains one of the fundamental coordinates describing where we belong within the vast architecture of our galaxy. Here, on a quiet lane of a sprawling cosmic city, the solar system completes its long journey through space. The solar system resides inside a small but significant structure of the Milky Way known as the Orion Spur, sometimes called the Orion Cygnus Arm. This region is not a full spiral arm but a minor, branching segment, a kind of cosmic bridge that stretches between two of the galaxy's major arms. The Sagittarius arm closer to the galactic center, and the Perseus arm farther outward. The Orion Spur is roughly 3,500 light-years wide and 10,000 light-years long, filled with a balanced mix of young, middle-aged, and old stars. It contains several prominent stellar nurseries, including the Orion Nebula, which gives the structure its name. Despite being only a minor feature in the Milky Way's architecture, the spur is unusually rich in star formation and molecular clouds, suggesting a dynamic local environment shaped by past supernovae and density waves passing through the galactic disk. Being positioned between two major arms is advantageous. The stellar density here is moderate, providing a relatively calm gravitational environment compared to the more crowded, high-energy interiors of the Sagittarius or Perseus arms. This reduces the likelihood of disruptive close encounters with massive stars or frequent supernova explosions. At the same time, the spur contains enough heavy elements and interstellar material to support the formation of Earth-like planets, conditions that would have been rarer in the metal-poor outer halo. Thus, Earth's local galactic neighborhood is a kind of cosmic suburb, peaceful, stable, and enriched by many generations of stars. It is neither too dense nor too empty, an ideal location for a planetary system to evolve over billions of years. The Sun, along with the entire solar system, moves through the Milky Way along a vast orbital path that encircles the galactic center. This journey is slow on a human timescale but swift in cosmic terms. Our star completes one full revolution every 225 to 250 million years, a period often called a galactic year. During each orbit, the Sun travels at an extraordinary speed, approximately 220 kilometers per second, yet because the galaxy itself is immense, the motion feels imperceptible to us. This orbit is not a perfect circle. It is slightly elliptical, and the solar system also oscillates up and down through the galactic disk roughly every 30 million years, passing through denser regions and then rising into thinner interstellar space. Each cycle subtly changes the radiation environment, the distribution of nearby molecular clouds, and the gravitational influences acting on the solar system. Despite the complexity of these motions, the Sun's orbit remains remarkably stable. Its velocity and radial distance place it in a relatively calm region of the Milky Way, far from the crowded, energetic galactic core and distant from the sparse, metal-poor outskirts. As we travel our enormous orbit, the solar system also moves relative to spiral arms, sometimes approaching regions thick with star formation, other times drifting between them. Altogether, the orbital motion of the Sun illustrates just how dynamic our place in the galaxy truly is. Earth and its neighboring planets ride through space on a path shaped by the Milky Way's gravity, tracing a slow, majestic arc around the supermassive black hole at the galaxy's heart. The central bulge of the Milky Way is the densely packed, ellipsoid-shaped heart of our galaxy, a region where gravity, age, and stellar history converge into a luminous, compact core. Unlike the graceful spiral arms filled with younger, blear stars, the bulge is dominated by old, metal-rich stars, many of which formed in the earliest eras of the Milky Way, more than 10 billion years ago. These stars are chemically evolved, containing heavier elements forged in multiple generations of supernovae, which tells us that this region underwent intense and rapid star formation early in the galaxy's life. Structurally, the bulge has a distinctive peanut or box-shaped form when viewed from certain angles, a signature of a bar-driven evolution. In fact, the bulge is not a perfect sphere but a slightly stretched, egg-shaped structure aligned with the Milky Way's bar. The density here is extreme. Stars are packed thousands of times closer together than in our local neighborhood. In some regions, the stellar density is so high that distances between stars can be measured in light weeks instead of light years. This central environment is dynamic and energetic. While the stars are old, their motions are rapid and complex, influenced by the galaxy's bar, the gravitational pull of the disk, and especially the enormous mass at the very center. The bulge contains vast clouds of gas and dust interwoven with dense clusters, including some of the oldest known globular clusters. Altogether, the bulge is a fossil of galactic history, a preserved remnant of the Milky Way's earliest phases. Its population of ancient stars, high central density, and distinctive shape make it a key region for understanding how spiral galaxies form, evolve, and sustain themselves across cosmic time. The central bar of the Milky Way is one of the most important structural features of our galaxy, a long, elongated band of stars, gas, and dust that stretches across the inner region like a cosmic spine. Modern infrared observations from telescopes such as Spitzer, WISE, and the VVV survey have conclusively confirmed its existence, revealing that the Milky Way is not a simple spiral galaxy but a barred spiral. This bar extends roughly 10,000 light-years from end to end, making it a dominant gravitational structure that shapes the motion of material in the inner galaxy. The bar is composed mainly of older, reddish stars, but it also channels large amounts of interstellar gas along its length. This flow of gas is not random. The bar acts like a gravitational engine, directing gas inward toward the central regions, where it can feed star formation and help maintain activity around the galactic nucleus. As a result, the bar plays a critical role in sustaining the Milky Way's internal evolution, driving cycles of star birth and influencing the morphology of the spiral arms that emerge from its tips. Its rotation is another defining trait. The bar spins as a coherent structure, affecting the orbits of stars around it, reshaping the distribution of matter within several thousand light-years of the center. It even helps sculpt the boxy or peanut-shaped appearance of the central bulge, illustrating how deeply interconnected the bar is with the galaxy's core architecture. In a broader sense, the bar is both an engine and a historic record, an active driver of galactic dynamics and a relic of past gravitational instabilities that formed it billions of years ago. Understanding the bar means understanding the heartbeat of the Milky Way itself. At the very center of the Milky Way lies one of the most remarkable objects in our cosmic neighborhood, the supermassive black hole Sagittarius A*, SGR-A*. Although invisible by its nature, no light can escape its gravity. Its presence is revealed with extraordinary clarity through the motion of nearby stars. Over the past 3 decades, observatories such as ESO's Very Large Telescope, VLT, and the Keck Observatory in Hawaii have tracked individual stars orbiting this dark, compact region. One star in particular, known as S2, completes an orbit in just 16 years, traveling at speeds of more than 7,000 kilometers per second when closest to the center. These orbits trace out perfect ellipses whose focal point contains an object with a mass of roughly 4.3 million suns, squeezed into a region no larger than our solar system. No known phenomenon other than a supermassive black hole can explain such extreme density and gravitational influence. SGR-A* is currently in a relatively quiet state, accreting only small amounts of gas and dust, which is why it does not shine as brightly as the black holes found in active galaxies. Still, the environment around it is energetic and turbulent, filled with hot plasma and fast-moving stellar remnants. In 2022, the Event Horizon Telescope, EHT, collaboration produced the first direct image of SGR-A*'s shadow by linking radio telescopes across the globe into a single Earth-sized virtual instrument. What emerged was a glowing, donut-shaped ring of emission surrounding a dark interior, the silhouette of the black hole's event horizon against the bright, heated material swirling around it. This image confirmed long-standing predictions from general relativity and provided a direct visual signature of the Milky Way's central gravitational anchor. Together, decades of stellar measurements and the groundbreaking EHT image give us a detailed, empirical picture of SGR-A star. It is the massive cornerstone of our galaxy's dynamic center, shaping the orbits of millions of stars in the bulge and silently influencing the evolution of the Milky Way as a whole. The Milky Way's spiral arms are not solid structures but vast, gravitationally sculpted regions where stars, gas, and dust crowd together into elongated, glowing lanes. These arms are density waves, patterns that move through the galactic disk and compress gas as they pass. That compression triggers star formation, which is why spiral arms shine with bright, young, blue stars and glowing nebulae. Although we cannot see the arms directly from inside the galaxy, radio mapping of hydrogen gas, infrared observations of dust, and precise star surveys, including Gaia, reveal their large-scale layout. The Milky Way structure is dominated by 4 major spiral arms, each extending tens of thousands of light-years and wrapping gracefully around the galactic disk. The Perseus arm is one of the most prominent, lying farther from the galactic center than the Sun and rich in massive star-forming regions. It contains a dense population of hydrogen clouds and is home to several well-known star clusters, making it a defining landmark in the outer galaxy. Closer to the center lies the Norma arm, one of the innermost major arms. It arcs around the core and contains some of the brightest and most active birthplaces of stars in the Milky Way. This region is heavily obscured by dust, but infrared observations reveal enormous molecular clouds and clusters forming deep inside. The Scutum Centaurus arm is another dominant structure, sweeping outward from near the bar and extending across vast distances of the disk. It is distinguished by massive star-forming complexes, including some of the largest known in the galaxy, and by dense molecular clouds that feed the formation of giant, short-lived stars. Finally, closer to our position lies the Sagittarius arm, which emerges from the ends of the bar and winds outward. Despite not being the arm in which the Sun resides, it plays a crucial role in shaping the environment of the inner galaxy. It contains numerous nebulae, including the famous Lagoon Nebula and the Trifid Nebula, making it one of the visually richest sectors of the Milky Way. Together, these arms create the grand spiral architecture that defines our galaxy. They are dynamic, evolving structures shaped by gravity, star formation, and the rotation of the disk itself, cosmic pathways where stellar generations rise and fade over billions of years. The Milky Way is not composed only of its grand, sweeping spiral arms. Between these major structures lie smaller, intricate features that add texture and complexity to the galactic disk. One of the most important of these is the Orion spur, the small spiral fragment in which the Sun resides. Rather than being a full arm, the Orion spur is a minor, intermediate structure, positioned between the much larger Sagittarius arm and Perseus arm. It stretches for several thousand light-years and contains a rich assortment of gas clouds, nebulae, and star-forming regions, including the Orion Molecular Cloud Complex, the Carina Cygnus armlets, and numerous young clusters. Its relative quietness, compared to the chaos of major arms, provides a stable environment in which the solar system has evolved for more than 4 billion years. The Orion spur is also a reminder that galactic structure is dynamic. Spiral arms are not rigid, permanent objects, but patterns in motion influenced by gravitational forces, gas flows, and density waves. Among the subtle features shaping these patterns are kinematic waves, large-scale oscillations in the disk created by gravitational interactions, the rotation of the bar, and the passage of density waves. These kinematic disturbances ripple through the stellar population, affecting star velocities and subtly altering the positions of gas clouds. Observations from surveys such as Gaia reveal that stars throughout the Milky Way move in gently undulating patterns, creating vertical and radial waves that oscillate across the disk. These waves can thicken or thin regions of the disk, shift pockets of gas, and even influence where new clusters form. Together, the Orion spur and the galaxy's kinematic waves illustrate the Milky Way's deeply alive and evolving nature. Our home is part of a constantly shifting lattice of gas, dust, and stars, a structure that breathes, ripples, and changes over cosmic time. Far from being static, The galaxy is a dynamic organism shaped by countless subtle gravitational rhythms. The disk of the Milky Way is the wide, rotating, star-filled plane that gives our galaxy its iconic spiral appearance. But this disk is not a single uniform structure. It is made of several distinct layers, each with its own stellar populations, chemistry, and history. The thin disk is the youngest and most vibrant component. It contains stars that are typically less than a few billion years old, including many massive blue stars that illuminate the spiral arms. This region is rich in metals, elements heavier than helium, because it has been enriched by countless generations of supernova explosions. The thin disk is also where most ongoing star formation occurs, fed by dense reservoirs of cold gas and dust. Nebulae, molecular clouds, and stellar nurseries populate this region, shaping its luminous and dynamic character. Above and below the thin disk lies the thick disk, a faint, extended layer composed mostly of older stars, some between 8 and 12 billion years old. These stars orbit the galaxy in slightly inclined, puffed-out trajectories compared to those in the thin disk, giving the thick disk a vertically stretched appearance. They also contain far fewer heavy elements, indicating they formed early in the Milky Way's history, before the galaxy had time to accumulate metals from repeated stellar deaths. The thick disk is a relic of the galaxy's formative period, possibly shaped by early mergers or internal gravitational instabilities. Threaded through both components are the gas layers that fuel star formation and trace the galaxy's structure. The warm, glowing H2 regions, clouds of ionized hydrogen, mark the places where massive young stars emit radiation energetic enough to strip electrons from hydrogen atoms. These nebulae are beacons of recent star birth. The cooler Hi layer, composed of neutral atomic hydrogen, forms a widespread, extended sheet that maps the spiral arms and acts as a reservoir for future star-forming material. Deeper still are the coldest and densest structures, molecular clouds, where hydrogen exists primarily as H. These clouds collapse under gravity to form new stars, forging the next generation of the galaxy's stellar population. Together, the thin disk, thick disk, and layered gas components form the complex, stratified architecture of the Milky Way's disk. They reveal a galaxy still growing, still evolving, and shaped by billions of years of cosmic history. The halo of the Milky Way is the galaxy's most ancient and ghostly component, an enormous, diffuse sphere that surrounds the disk and stretches far beyond the visible stars. Unlike the bright, structured spiral arms, the halo is faint, sparse, and populated by some of the oldest stars in existence. Many of them formed more than 12 to 13 billion years ago, shortly after the birth of the galaxy itself. These stars are metal poor, meaning they contain extremely small amounts of elements heavier than helium. Their primitive chemical composition reveals that they were born before supernovae enriched the galaxy with heavier elements, making them precious fossils of the early universe. Scattered throughout this region are globular clusters, dense, spherical gatherings of tens of thousands to millions of stars bound tightly together by gravity. More than 150 such clusters orbit the Milky Way within the halo, moving on long, elliptical paths that sweep far above and below the galactic disk. These clusters are among the oldest structures in the galaxy, with many dating back nearly to the beginning of cosmic time. Their compact nature and uniform age make them crucial tools for studying the Milky Way's formation, its early mergers, and its long-term evolution. However, the most significant component of the halo is something we cannot see directly: dark matter. Observations of stellar motions reveal that stars in the outer regions of the galaxy orbit far too quickly to be held in place by the visible mass alone. The rotation curve of the Milky Way remains flat at great distances from the center, a signature that a vast, unseen mass surrounds the galaxy. This mass, estimated to be about 1 to 1.6 trillion solar masses in total, forms a gigantic dark matter halo that extends hundreds of thousands of light-years in every direction. Dark matter provides the gravitational scaffolding that holds the galaxy together and explains why the halo's ancient stars and globular clusters remain bound despite their enormous orbits. Together, the old stars, globular clusters, and dark matter transform the halo into a living archive of the galaxy's history, a silent, extended structure that preserves the memory of the Milky Way's earliest epochs while shaping its future through gravity that we feel but cannot see. The Milky Way is home to a staggering diversity of stars, each type reflecting a different stage of stellar evolution, a different chemical history, and a different role in shaping the galaxy's long-term development. The most common of all are red dwarfs, small, cool, and faint stars that make up the majority of the stellar population. Although individually dim and difficult to observe over large distances, red dwarfs are extraordinarily long-lived, often surviving for trillions of years. Their sheer abundance forms the quiet backbone of the galaxy, filling the disk and halo with countless dim points of light. Next are the sun-like stars, often called G-type or main sequence stars. These stars are more massive and brighter than red dwarfs, and their relatively stable lifetimes of several billion years make them ideal hosts for complex planetary systems. Though far less numerous than red dwarfs, they are among the most important for understanding the evolution of habitable environments and the chemical enrichment of the galaxy. The Milky Way also contains a smaller but spectacular population of giants and supergiants, massive, luminous stars that live fast and die young. These bright, blue or red stars dominate star-forming regions and spiral arms. Their powerful winds and explosive deaths as supernovae recycle heavy elements, including carbon, oxygen, silicon, and iron, into the interstellar medium. This enrichment contributes to the next generations of stars and planets, gradually increasing the metal content of the galaxy over billions of years. Among the oldest inhabitants of the Milky Way are population II stars, which formed when the universe was still young. These stars are typically found in the halo, bulge, and globular clusters, and are defined by their very low metallicity, evidence that they were born before the galaxy had undergone significant chemical enrichment. Many of them are more than 10 to 12 billion years old, marking them as survivors from the earliest epoch of the Milky Way's formation. Together, these stellar populations define the galaxy's past and future. Young stars illuminate the spiral arms, old stars preserve the history of ancient epochs, and massive stars drive the chemical evolution that makes planets and life possible. The Milky Way's stellar diversity is not just a collection of cosmic objects. It is an unfolding story of creation, transformation, and renewal across cosmic time. The interstellar medium of the Milky Way, its gas and dust, is the raw material from which stars, planets, and entire systems are born. Although it makes up only a small fraction of the galaxy's total mass, this mixture of molecules, atoms, and microscopic grains plays an outsized role in shaping galactic evolution. At the heart of this ecosystem lie molecular clouds, enormous cold reservoirs primarily composed of molecular hydrogen, H. Because H is difficult to detect directly, astronomers often trace these clouds using carbon monoxide, CO, whose emission lines clearly reveal the structure of the densest star-forming regions. These clouds can span hundreds of light-years and contain enough mass to form thousands of new stars. Within them, gravity slowly gathers material into tighter knots. As these knots collapse, they heat up and eventually ignite as new stars. Molecular clouds represent the quiet, cold beginnings of stellar life. In contrast, H2 regions are bright, glowing zones where young massive stars have already formed. Their intense ultraviolet radiation ionizes the surrounding hydrogen gas, stripping electrons from atoms and producing the characteristic red or pink emission visible in nebulae. These regions often outline the spiral arms, marking the locations of recent star formation. They are active, dynamic environments where stellar winds, radiation, and supernovae carve complex shapes into the surrounding gas, triggering new waves of collapse and renewal. Some of the most striking examples of star formation in the Milky Way are massive star-forming complexes, such as the Carina Nebula. Located thousands of light-years away, Carina is one of the largest and brightest nebulae in the galaxy. It contains towering molecular pillars, hot young clusters, and some of the most massive known stars, including Eta Carinii. Within this nebula, the interplay of gravity, shock waves, and intense radiation sculpts the gas into dramatic forms while continually giving birth to new stellar generations. Interstellar dust, tiny grains of carbon, silicates, and ices, threads through all of these environments. Though dust makes up only about 1% of the interstellar medium by mass, it profoundly influences the galaxy by absorbing starlight, shielding molecular clouds from radiation, and enabling chemical reactions on its surfaces. Without dust, molecular hydrogen, the foundation of star formation, could hardly form. Together, molecular clouds, H2 regions, and star-forming complexes form the dynamic cycle of stellar birth and transformation. They are the living, breathing component of the Milky Way, shaping its structure and fueling its evolution on cosmic scales. One of the most profound discoveries in modern astronomy is that the Milky Way, like all large galaxies, is dominated not by the stars and gas we can see but by an invisible form of matter known as dark matter. Its presence is not speculative. It is required by multiple independent lines of observational evidence, the strongest of which comes from the rotation curves of stars. When astronomers measure how fast stars move around the center of the galaxy, they expect that stars farther from the center should orbit more slowly, just as planets move more slowly the farther they are from the sun. But that is not what the data show. Instead, when scientists plot a rotation curve, a graph of orbital velocity versus distance, they find that the curve remains flat far beyond the visible disk. Stars in the outer regions orbit at nearly the same speed as those much closer to the center. This behavior cannot be explained by the gravitational pull of visible matter alone. The Milky Way simply does not contain enough luminous mass, stars, gas, dust, to hold itself together at these high orbital speeds. Without an additional, unseen source of gravity, the galaxy would fly apart. This discrepancy is the strongest evidence that the Milky Way is surrounded by a vast halo of dark matter, whose mass outweighs the visible components by a factor of 5 or more. Dark matter does not emit, absorb, or reflect light, making it impossible to observe directly with conventional telescopes. But its gravitational influence is unmistakable. It shapes the motions of stars, stabilizes the galactic disk, and determines how the Milky Way interacts with its satellite galaxies. Simulations show that without dark matter, the Milky Way could not have formed in its present structure, nor could it maintain its spiral shape over billions of years. Today, the Milky Way's total mass is estimated at around 1 to 1.6 trillion solar masses, and the overwhelming majority of that mass must be dark matter. Although we do not yet know its true nature at the particle level, its gravitational fingerprint is one of the most solid, consistent, and essential facts in modern astrophysics. Dark matter is not just something the Milky Way contains. It is the invisible framework that holds the galaxy together, shapes its evolution, and allows all visible components to exist in their present form. At the very heart of the Milky Way lies its most extreme and defining object, Sagittarius A*, the supermassive black hole that anchors the entire galaxy. Though completely invisible in ordinary light, its presence is revealed through the extraordinary motions of stars that will around it at breathtaking speeds. Sagittarius A* functions as the gravitational center of the Milky Way, a compact object containing roughly 4.3 million times the mass of the Sun compressed into a region no larger than the orbit of Mercury. The existence of Sagittarius A* was first suspected in the 1970s, when astronomers detected an intense and compact radio source in the direction of the Sagittarius constellation. Over time, increasingly precise measurements confirmed that this radio source had to be something extraordinarily dense. The breakthrough came in the 1990s and early 2000s, when teams at the Keck Observatory and the European Southern Observatory began tracking the orbits of individual stars in the galactic center. These so-called S-stars follow tight, rapid, highly elliptical paths, completing full orbits in just a few years, far faster than any typical star cluster could explain. The most dramatic example is S2, a bright star that swings extremely close to Sagittarius A* every 16 years. During its closest approach, S2 travels at more than 7,600 kilometers per second, or nearly 3% of the speed of light. Only a supermassive black hole could generate such powerful gravitational forces. These stellar motions provided direct, irrefutable evidence that a massive, compact object sits at the galactic center. In 2022, the Event Horizon Telescope, EHT, delivered the most iconic image of Sagittarius A*, a glowing, donut-shaped ring of light created by radiation from hot gas swirling around the event horizon. This image was not a photograph in the traditional sense, but a reconstruction based on synchronized radio observations from telescopes around the world. What it revealed matched perfectly with predictions of general relativity, a dark, circular shadow surrounded by a bright, asymmetric ring produced by gravitational lensing and relativistic effects. Despite its enormous mass, Sagittarius A** is surprisingly quiet compared to the supermassive black holes found in active galaxies. It consumes matter sporadically, producing occasional flares in X-ray and infrared light. In terms of cosmic behavior, it currently resides in a relatively dormant phase. However, evidence of past activity remains imprinted in the galaxy. The giant Fermi bubbles, two massive lobes of high-energy gas extending tens of thousands of light-years above and below the Milky Way, may be relics of a powerful outburst from Sagittarius A* millions of years ago. The environment around the black hole is one of the most extreme regions in the Milky Way: dense clusters of young stars, turbulent clouds of ionized gas, magnetic fields twisted by rapid motion, and shockwaves from frequent stellar deaths. Yet all of this orbits a gravitational abyss from which not even light can escape. Sagittarius A* is more than just a point in space. It is the defining anchor of our galaxy's architecture. It influences star formation in the central region, shapes gas flows, and stabilizes the overall gravitational potential of the Milky Way. Every orbiting star, every dust cloud, every spiral arm ultimately traces its motion around this single, massive object. To understand Sagittarius A* is to understand the deep structure and evolution of the Milky Way itself, the beating heart of the galaxy we call home. While Sagittarius A* dominates the galactic center, the rest of the Milky Way is populated by hundreds, and very likely thousands, of smaller stellar mass black holes scattered throughout the disk. These objects are the remnants of massive stars that ended their lives in powerful core collapse supernovae. Unlike the supermassive giant in the center, these black holes are silent, faint, and extremely difficult to detect. Most drift unnoticed through the galaxy, invisible unless they interact with nearby stars or gas. Stellar mass black holes typically contain 5 to 20 times the mass of the Sun, though some exceptional ones reach 30 or even 60 solar masses. Over billions of years, the Milky Way has produced an enormous number of massive stars, especially in the spiral arms and regions of intense star formation. When these stars died, they left behind black holes that became integrated into the galactic disk. Theoretical models suggest that the Milky Way should contain over 100 million stellar mass black holes in total, though only a tiny fraction have been detected directly. When astronomers refer to hundreds, they mean the confirmed systems, the ones we can actually measure and study, but the real population is vastly larger, hiding in the darkness. The confirmed stellar black holes are usually discovered in X-ray binary systems, where a black hole orbits a normal star. As matter from the companion star is pulled toward the black hole, it heats up and emits bright X-rays, revealing the presence of the otherwise invisible object. Cygnus X1 is the most famous example, one of the first suspected black holes in history, and one of the brightest X-ray sources in the sky. However, many black holes do not possess companion stars or accretion disks, making them completely dark and nearly impossible to detect. In recent years, gravitational microlensing has become a powerful tool for discovering isolated black holes. When a black hole passes in front of a distant star, its gravity bends and magnifies the star's light. This produces a characteristic brightening that can be measured even if the black hole emits no radiation. Using this method, astronomers have now confirmed the existence of several solitary black holes drifting through the Milky Way's disk, quiet, invisible travelers that reveal themselves only through their gravitational pull. These small black holes are not distributed randomly. Many are concentrated in the spiral arms, where massive stars form and die. Some move rapidly through the disk after receiving a kick from the asymmetric explosion of the supernova that created them. Others remain in clusters or associations, still near the regions where they were born. A few are even thought to wander into the halo or escape the galaxy entirely due to these supernova kicks. The presence of so many black holes affects the galaxy on subtle but important scales. Their gravitational interactions can influence the dynamics of star clusters, alter the structure of binary systems, and contribute to the overall mass distribution of the disk. Moreover, they serve as crucial test beds for understanding the final stages of stellar evolution. With new observatories such as the Nancy Grace Roman Space Telescope and future gravitational wave detectors, the population of known stellar black holes is expected to grow dramatically in the coming decades. In reality, the Milky Way is not simply sprinkled with stars, it is filled with unseen remnants. These hundreds of confirmed black holes, and the millions more predicted to exist, are silent witnesses to the galaxy's past, drifting through space in the shadows of the spiral arms that gave birth to them. Among the most important and revealing objects in the Milky Way are X-ray binary systems, pairs of stars in which one member is a compact, collapsed object such as a black hole or a neutron star. These systems are astrophysical laboratories, letting us observe extreme physics that cannot be reproduced on Earth. What makes them unique is their intense emission of high-energy X-rays, produced when material from the normal star is drawn toward the compact object and heated to extraordinary temperatures, often tens of millions of degrees, before crossing the event horizon or striking a neutron star's surface. An X-ray binary begins its life when a massive star in a binary pair collapses into a neutron star or black hole after a supernova. If the system survives the violent explosion and remains gravitationally bound, the compact remnant can begin to pull material from its companion star. This process, called accretion, forms a rotating disk of gas spiraling inward, known as an accretion disk. Friction and gravitational energy heat this disk to immense temperatures, causing it to emit strong X-rays detectable across the galaxy. For astronomers, this X-ray light is like a beacon that reveals the presence of an otherwise invisible compact object. There are two major categories of X-ray binaries. High-mass X-ray binaries, HMXBs, contain a young, massive, hot star, often an O or B-type star many times heavier than the Sun, paired with a black hole or neutron star. These massive companions lose large amounts of matter through stellar winds, which the compact object captures. Systems such as Cygnus X1 and Vela X1 belong to this group. HMXBs are typically found in the spiral arms of the Milky Way, where young, massive stars form. They are powerful but short-lived, burning brightly before their massive stars evolve and explode. The second class is low-mass X-ray binaries, LMXBs, where the companion star is smaller, usually similar to or lighter than the Sun. In these systems, matter is transferred through a more stable process called Roche-Lobe overflow, where the smaller star fills its gravitational boundary and funnels material toward the compact object. Because low-mass stars live much longer, LMXBs can persist for billions of years. Many are found in the central bulge of the Milky Way or in globular clusters, environments densely packed with old stars. Some LMXBs transition into millisecond pulsars, neutron stars spun up to phenomenal speeds by the angular momentum of the accreted material. X-ray binaries are also a key source of jets, narrow, fast streams of material launched perpendicular to the accretion disk. In systems called microquasars, such as GROJ 1655-40 or SS433, these jets travel at relativistic speeds, sometimes close to the speed of light. They mimic the behavior of supermassive black holes in distant galaxies, but on a much smaller scale, allowing astronomers to study these extreme processes up close. Because X-ray binaries are bright and energetic, they help map the structure of the Milky Way. Their distribution reveals patterns of star formation, stellar evolution, and the regions where compact objects are most common. Observatories such as Chandra, XMM Newton, and NICER continue to discover new systems, refine measurements of known ones, and observe the violent flares and outbursts produced when accretion suddenly increases. In many ways, X-ray binaries are the lighthouses of the Milky Way, blazing signatures of gravity, magnetism, and extreme matter. Through them, we study the deaths of massive stars, the birth of black holes and neutron stars, and the extraordinary physics that occurs when ordinary matter encounters the most compact objects in the universe. Supernova remnants are among the most dramatic and scientifically valuable structures in the Milky Way, and two of the most iconic examples are the Crab Nebula and the Vela supernova remnant. These objects are the expanding remains of massive stars that ended their lives in violent explosions, leaving behind intricate clouds of gas, shockwaves, and dense stellar cores. Studying these remnants offers a rare window into the physics of stellar death, particle acceleration, and the recycling of material that ultimately forms new generations of stars and planets. The Crab Nebula, also known as Messier 1, is the remnant of a supernova observed on Earth in the year 1054 AD, recorded by Chinese, Japanese, and Arab astronomers. What they witnessed as a star so bright it was visible during the day for weeks is now a rapidly expanding cloud of ionized gas and magnetic filaments roughly 6,500 light-years away in the constellation Taurus. The structure of the Crab Nebula is exceptionally complex. Long, thread-like filaments trace the remains of the star's outer layers, consisting largely of ionized hydrogen, helium, oxygen, nitrogen, and other elements produced during the star's life and death. These filaments surround a glowing interior powered by a dense neutron star at the center. At the heart of the Crab Nebula lies the Crab Pulsar, a rapidly rotating neutron star only about 25 kilometers across, but with a mass greater than that of the Sun, spinning about 30 times per second. It emits beams of radiation that sweep across space like a lighthouse. The pulsar generates an enormous magnetic and particle wind, a stream of ultra-relativistic electrons and positrons, which fills the nebula and causes it to shine intensely in radio, optical, X-ray, and gamma-ray wavelengths. The Crab Nebula is one of the most studied astrophysical objects in the universe and serves as a natural laboratory for understanding extreme magnetic fields, particle acceleration, and high-energy astrophysics. The Vela supernova remnant is significantly older than the Crab Nebula, with an estimated age of around 11,000 years. Located approximately 800 light-years away in the constellation Vela, it is one of the closest known remnants to Earth. Because it has expanded for thousands of years longer than the Crab Nebula, it covers a far larger region of the sky, spanning roughly 8 degrees, equivalent to 16 full moons side by side. Unlike the Crab Nebula's dense interior, the Vela remnant is a large, intricate bubble of shock-heated gas and tangled filaments spreading through the interstellar medium. Like the Crab Nebula, the Vela remnant also contains a neutron star, the Vela pulsar, spinning about 11 times per second. The pulsar emits powerful jets and a pulsar wind nebula, visible in X-rays as arcs and knots shaped by the neutron star's magnetic field. Because of its proximity, the Vela remnant provides an exceptional opportunity to study how supernova blast waves propagate, how they sweep up interstellar gas, and how they create turbulence, magnetic structures, and shock fronts that can trigger the formation of new stars in nearby clouds. Supernova remnants like these play a crucial role in the evolution of the Milky Way. They enrich the galaxy with heavy elements synthesized inside massive stars: carbon, oxygen, silicon, iron, which later become part of planets, life, and future stellar systems. They also inject energy into the interstellar medium, stirring and heating it, and influencing the distribution of gas across the galaxy. By observing remnants from different ages and distances, astronomers trace the full cycle of stellar evolution, from birth to catastrophic destruction, and onward to the creation of new cosmic structures. Together, the Crab Nebula and the Vela remnant highlight two different stages of a supernova's aftermath: the youthful, energetic, pulsar-driven glow of the Crab, and the vast, cooling, shock-sculpted shell of the older Vela remnant. Both remain essential to our understanding of how stars end their lives and how their explosive deaths shape the Milky Way on both small and galactic scales. The Milky Way is still an actively star-forming galaxy, though not nearly as intense as it was in its early youth billions of years ago. Today, astronomers estimate that our galaxy produces roughly 1 to 2 new stars per year, a value derived from measurements of gas content, the luminosity of star-forming regions, and the distribution of massive, short-lived stars that trace recent stellar birth. This number may sound small compared to the hundreds of billions of stars already present, but it represents a balanced, steady rate typical of a mature spiral galaxy. The current pace of star formation is governed primarily by the amount of cold molecular gas available, since stars cannot form unless clouds of hydrogen cool enough to collapse under gravity. Observations show that the Milky Way contains several billion solar masses of such gas, concentrated in large molecular complexes scattered throughout the spiral arms. These clouds occasionally undergo gravitational instabilities, producing dense cores that fragment into clusters of new stars. Not all regions of the Milky Way contribute equally. Most new stars are born in the thin disk, especially along the major spiral arms where density waves compress gas into elongated lanes. The Sagittarius arm, the Perseus arm, the Scutum Centaurus arm, and the Norma arm all host clusters of bright, massive, blue stars that act as beacons of recent star formation. Meanwhile, the Orion Spur, our local region, contains active nurseries such as the Orion Molecular Cloud Complex, where astronomers can study stellar birth up close. The measured rate of 1 to 2 stars per year reflects the long-term average. In smaller pockets, the process can be far more dramatic. Large nebulae like Carina, Cygnus X, and W43 produce stars at rates that dwarf the galactic average, generating massive stellar clusters, O-type giants, and powerful winds that sculpt the surrounding environment. These regions illustrate that star formation is not uniform, but occurs in bursts triggered by feedback, turbulence, spiral arm compression, or even shock waves from earlier supernovae. Modern telescopes, particularly ALMA, Gaia, Spitzer, and the JWST, allow astronomers to quantify star formation rates by observing the faint thermal glow of dust, the radio emissions from molecular gas, and the ultraviolet light from young, hot stars. All lines of evidence converge on the same conclusion. The Milky Way is neither a starburst galaxy nor a dying one. Instead, it exists in a healthy, stable middle age, turning gas into stars at a moderate pace that can continue for billions of years. This ongoing cycle replenishes stellar populations, enriches the galaxy with heavier elements, and maintains the dynamic, evolving structure we observe today. Some of the most intense and scientifically valuable star-forming environments in the Milky Way are concentrated in a few exceptionally active regions. Among them, Cygnus X, the Carina Nebula, and the Perseus molecular cloud stand out as powerful engines of stellar birth, each at a different scale and evolutionary stage. Together, they reveal how gas, dust, turbulence, gravity, and feedback interact to shape the next generation of stars in our galaxy. Cygnus X is one of the most massive and luminous star-forming complexes in the entire Milky Way, located roughly 4,500 light-years away in the constellation Cygnus. It spans hundreds of light-years and contains an enormous concentration of dense molecular gas and young clusters. What makes Cygnus X remarkable is its combination of extremely massive O-type and B-type stars, embedded protostars still wrapped in dust, and giant bubbles carved out by intense stellar winds and radiation. At its core lies the Cygnus OB2 Association, one of the largest known groups of massive stars in the galaxy, containing dozens of hot, luminous giants whose energy shapes the entire region. The powerful ultraviolet radiation excavates cavities in the surrounding gas, triggering further collapse along the denser edges. Cygnus X is essentially a living demonstration of triggered star formation, where one generation of stars initiates the birth of the next through shock fronts, stellar winds, and feedback-driven turbulence. The Carina Nebula, located about 7,500 light-years away, is another of the Milky Way's star-forming giants, though even more visually dramatic. It is home to some of the most massive and energetic stars ever observed, including the famous luminous blue variable Eta Carinii, a stellar titan hundreds of times more massive than the Sun and millions of times more luminous. Carina is filled with towering pillars, sculpted dust formations, expanding bubbles, and intense HII regions glowing with ionized hydrogen. The density contrasts in the nebula reveal regions of active collapse, with young stars emerging from cocoons of dust while jets from newborn protostars carve delicate channels through the surrounding medium. Massive star feedback, winds, radiation pressure, and ancient supernova remnants has broken the nebula into complex substructures, making it an ideal laboratory for studying how large-scale turbulence interacts with star-forming cores. Because of its proximity and brightness, Carina remains one of the richest fields for observing all evolutionary stages at once, from cold molecular knots, to young clusters, to supermassive stars reaching the end of their lives. The Perseus molecular cloud, at about 1,000 light-years away, represents a smaller and more serene, yet still highly productive region of star formation. It stretches roughly 500 light-years and contains several well-studied clusters, including IC348 and NGC 1333. Unlike the violent, feedback-dominated environments of Cygnus X and Carina, Perseus is a gentler star-forming nursery dominated by low-mass star formation. It is rich in dense, cold filaments where gravity slowly pulls gas together into protostars and young stellar objects. Numerous jets, bipolar outflows, and molecular shocks trace the early stages of collapse. Because of its relative transparency and proximity, the Perseus cloud has become a cornerstone for understanding the birth of sun-like stars and protoplanetary disks. Modern observations from ALMA, Spitzer, and Herschel have mapped its filaments in exquisite detail, showing how turbulence fragments the gas into long strands that become the seeds of future clusters. Although these regions differ in scale and intensity, they collectively illustrate the diversity of star-forming environments in the Milky Way. Cygnus X demonstrates the extreme end of cluster formation powered by massive stars. The Carina Nebula shows the interplay of violent feedback with rapid stellar birth, and the Perseus Cloud highlights the quieter processes that produce the majority of sun-like stars. Together, they paint a complete picture of how the Milky Way continues to transform its gas into new stars, from gentle nurseries to explosive, high-energy stellar factories. Star clusters play a central role in our understanding of stellar evolution because they form from the same molecular cloud at roughly the same time and with similar initial compositions. This makes them natural laboratories for observing how stars of different masses develop under shared conditions. Within the Milky Way, several cluster regions stand out as essential benchmarks: the Pleiades, the Hyades, and the massive young cluster NGC 3603. Each represents a different age group, mass range, and evolutionary stage, offering a broad perspective on how star clusters form, evolve, and disperse over time. The Pleiades, also known as Messier 45, are one of the most recognizable and well-studied open clusters in the night sky. Located approximately 440 light-years away in the constellation Taurus, the Pleiades are a relatively young cluster, with an age of about 100 million years. The stars are dominated by bright, hot, blue-white types, particularly B-type stars that still shine with the intensity of youth. Because the cluster has not yet dispersed, its members remain gravitationally bound and concentrated into a tight grouping easily visible without telescopes. Surrounding the cluster is a faint reflection nebula, the result not of the star's own birth cloud, but of interstellar dust through which the Pleiades are currently passing. This dust reflects the blue light of the cluster's hottest stars, producing the characteristic shimmering glow seen in long-exposure images. The Pleiades serve as a cornerstone for calibrating stellar ages, rotation rates, and disk evolution in young stars. The Hyades, located about 150 light-years away in Taurus, represent a more mature stage of cluster evolution. With an age of roughly 600 to 700 million years, they are the nearest rich open cluster to Earth and have been crucial for mapping the Hertzsprung-Russell diagram with precision. Unlike the concentrated Pleiades, the Hyades have begun to disperse, forming a more extended, V-shaped grouping dominated by orange and yellow stars. Their proximity allows astronomers to measure distances to individual members with extraordinary accuracy, which in turn helps refine stellar evolution models. The Hyades also demonstrate how open clusters gradually dissolve into the galactic disk, losing members to tidal forces and internal dynamical interactions. Despite being older and less compact, they remain one of the most important benchmark clusters for studying intermediate-age stellar populations. At the opposite end of the spectrum lies NGC 3603, one of the most massive and active young star clusters in the Milky Way. Located about 20,000 light-years away in the Carina Sagittarius arm, NGC 3603 is often compared to the famous R136 cluster in the Large Magellanic Cloud due to its extraordinary density of massive stars. The cluster is embedded within a giant HII region shaped by powerful winds, radiation pressure, and the intense ultraviolet light from dozens of O-type stars and several of the most massive known stars. These young giants sculpt the surrounding gas into turbulent pillars, arcs, and cavities, creating one of the most visually dramatic star-forming environments in the galaxy. Because NGC 3603 is only about 1 to 2 million years old, astronomers can observe the earliest phases of cluster evolution and massive star formation in real time. Its extreme environment provides insight into how starburst regions operate and how massive stars shape their surroundings through feedback. Together, the Pleiades, Hyades, and NGC 3603 trace an evolutionary sequence, from very young clusters filled with hot, luminous stars, to mid-aged clusters undergoing gradual dispersal, to extreme, dense starburst clusters dominated by some of the galaxy's most powerful stellar giants. By studying these regions, astronomers can reconstruct the life cycle of clusters and better understand the processes that govern stellar birth, aging, and dissolution across the Milky Way. One of the most significant and inevitable events in the future of the Milky Way is its predicted interaction and eventual merger with the Andromeda Galaxy. Based on current measurements of radial velocity, proper motion, and gravitational modeling, astronomers estimate that in approximately 4 to 5 billion years, the two largest galaxies of the local group will begin a long, complex gravitational dance that ultimately reshapes both systems. This is not speculation but a prediction grounded in precise observations from the Hubble Space Telescope and the Gaia mission, which have measured Andromeda's motion through space with unprecedented accuracy. Despite the vast distance between them today, around 2.5 million light-years, the Milky Way and Andromeda are gravitationally bound and moving toward one another at roughly 110 kilometers per second. As dark matter halos overlap, the gravitational pull will accelerate, and the first meaningful interaction will involve the outskirts of the galaxies, the halos, stellar streams, and diffuse gas envelopes. This initial encounter will not be a sudden crash, but a slow interpenetration as tidal forces stretch both galaxies, creating elongated streams of stars that arc outward like wings. These tidal tails will carry stars tens of thousands of light-years from their original locations, marking the first visible signs of galactic transformation. Over the next several hundred million years, Andromeda will pass through the Milky Way and then swing back, creating a second and possibly third passage. Each encounter will dramatically disturb the structure of both disks. Spiral arms will warp, twist, and eventually break apart, replaced by enormous plumes of gas and stars. Gas clouds will be compressed during these interactions, triggering intense bursts of star formation, far higher than the present rate of either galaxy. These starburst phases may light up the interacting system with brilliant clusters of young, massive stars. Although the merger sounds catastrophic, the probability of individual stars colliding is extraordinarily low because of the immense distances between them. Instead, the orbits of stars will be reshaped on galactic scales. The Sun, if still intact at that time, may be flung outward into a more distant orbit or inward toward the galactic center, depending on the local gravitational environment during the encounters. However, none of these outcomes involve the Sun physically striking another star. The primary effects will be orbital migration, shifts in trajectory, and changes to the galactic architecture around it. After roughly 1 to 2 billion years of repeated passages, the gravitational energy of the system will dissipate, and the Milky Way and Andromeda will finally settle into a single, stable structure. Most simulations predict the formation of a large elliptical or lenticular galaxy, sometimes nicknamed Milkomeda. The original spiral disks will no longer exist in their familiar forms. Instead, the merged galaxy will possess a smoother, rounder stellar distribution, with a dense central region containing the combined mass of both original supermassive black holes. These black holes, Sagittarius A** in the Milky Way and Andromeda's central black hole, will spiral inward over time, eventually merging in a colossal release of gravitational waves. This future merger is not a destructive end, but a natural evolutionary step in the life of large galaxies. Many giant ellipticals observed in the universe today formed through exactly such processes. The interaction between the Milky Way and Andromeda will be one of the most dramatic transformations our galaxy will ever undergo, reshaping its structure, redistributing its stars, and ultimately leaving behind a new kind of cosmic home for whatever remains of the solar system. Through careful observation and modeling, astronomers now understand that this event is not merely possible, it is a fundamental part of the destiny of both galaxies. When the Milky Way and Andromeda finish their long gravitational interaction, the ultimate result will be the formation of a new, larger galaxy, most likely an elliptical or lenticular system. This conclusion comes from detailed computer simulations and from observations of similar mergers across the universe. The transformation is driven by the physics of gravitational relaxation, tidal forces, violent orbital mixing, and the dissipation of angular momentum. Over the course of roughly 1 to 2 billion years after their first close encounter, the original spiral structures of both galaxies will become increasingly distorted until they finally dissolve into a more rounded and dynamically stable configuration. Spiral galaxies like the Milky Way and Andromeda depend on the orderly rotation of their disks to maintain their characteristic patterns of arms, bars, and gas lanes. However, during a major merger, this rotational structure is disrupted. Stars experience large gravitational perturbations, which scatter them into random orbits rather than circular ones. As billions of stars are redistributed in this way, the disk thickens, stretches, and eventually loses its coherent shape. Gas clouds, driven by tidal compression and shocks, collapse rapidly and trigger intense starburst episodes, temporarily brightening the merging system. But as the gas supply is consumed or heated by feedback from massive stars and supernovae, star formation gradually subsides. Once the chaotic interactions settle, the merged galaxy will likely resemble the giant elliptical galaxies observed in many clusters today. These galaxies have smooth, rounded profiles, with stars moving in a wide range of random directions rather than aligning along a thin disk. Their central regions are dense and bright, often containing supermassive black holes that have themselves merged after spiraling together. Simulations show that the combined mass of Sagittarius A* and Andromeda's central black hole will eventually form a single, much larger black hole, releasing powerful gravitational waves during the merger process. The resulting galaxy's core will possess a deep gravitational potential well, giving it a characteristic glow concentrated toward the center. There is also the possibility that the final structure will be lenticular, S0, rather than fully elliptical. Lenticular galaxies occupy an intermediate category. They have a central bulge and a faint disk-like envelope, but lack substantial spiral structure or star-forming regions. This would occur if some fraction of the post-merger gas survives long enough to settle into a new rotating plane. However, because both Andromeda and the Milky Way will likely exhaust or heat much of their gas during the starburst phases, most models favor a primarily elliptical outcome. Whatever the exact final morphology, the new galaxy will be vastly different from either of the original spirals. It will be larger, more massive, and dominated by older stars once the starburst phase fades. Its halo will contain an intricate blend of stellar streams and remnants from both galaxies' satellite systems, now fused into a single gravitational domain. Over billions of years, these structures will slowly phase mix, leaving behind a smooth, extended stellar halo surrounding the central body. This transformation is not an anomaly but a natural evolutionary path. Many of the universe's biggest and brightest galaxies owe their existence to similar mergers. The future Milky Way or Andromeda remnant will be one more example, a cosmic monument to the forces of gravity, time, and stellar evolution, sculpted over hundreds of millions of years into a single, unified galaxy that bears little resemblance to the spirals we know today. The future of the solar system during the merger between the Milky Way and Andromeda is a subject that astronomers can model with remarkable confidence. Although the event sounds catastrophic, the actual experience for our planetary system will be far more subtle. The most important point is that direct collisions between stars are extraordinarily unlikely, even during a galactic merger. Stars are separated by such vast distances that, statistically, the Sun will almost certainly pass through the interactions unscathed. However, this does not mean the solar system will remain where it is. Its orbit will change dramatically as gravitational forces reshape the entire structure of the merging galaxies. Today, the Sun orbits the center of the Milky Way at a distance of about 27,000 light-years, following a fairly stable, nearly circular path. During the merger, this orbit will be influenced by the rapidly shifting gravitational landscape. As Andromeda's mass approaches, the combined gravitational potential of both galaxies will begin to dominate, tugging the Sun into a new trajectory. Simulations show that the Sun may be thrown outward into a much larger orbit, possibly 2 or 3 times farther from the center than it is now. In other scenarios, it may migrate inward or become part of a broad, elongated loop that oscillates through the emerging galaxy's interior. The exact path depends on the Sun's position and velocity at the time of each close encounter between the galaxies. Even though no stars will strike the Sun directly, the solar system will experience tidal gravitational forces, which may subtly perturb the orbits of distant objects such as comets in the Oort cloud. These disturbances could send some icy bodies toward the inner solar system, increasing comet activity over tens of millions of years. The planets themselves, however, remain securely bound to the Sun. The gravitational pull of our star is far stronger than any external stellar encounter we are likely to experience during the merger. By the time the Milky Way and Andromeda settle into a single massive elliptical galaxy, the Sun will be billions of years older. Within roughly 5 to 7 billion years, independent of the merger, the Sun will naturally evolve into a red giant, dramatically altering or engulfing the inner planets. This stellar evolution will shape the solar system's fate far more profoundly than the merger itself. In fact, the Sun's transformation into a red giant may already be advanced or complete by the time the final stages of the merger occur. One intriguing possibility from simulations is that the Sun may end up in a much darker, less populated region of the merged galaxy, far from dense star-forming environments. If it is flung outward, our night sky could become more barren, with fewer bright stars visible. In contrast, if the Sun is drawn inward toward the dense central regions of the remnant galaxy, the night sky could become extraordinarily bright, filled with countless stars packed into the core. Both outcomes are scientifically plausible, though the outward migration scenario is somewhat more likely. Ultimately, the key fact is that the solar system will survive the galactic merger, even as its orbit is reshaped beyond recognition. The collision of two galaxies does not imply the destruction of their stars. Instead, it is a process of gravitational reorganization on a grand scale. The Sun and its planets will continue to orbit peacefully around their star, even as the galaxy around them is transformed into something entirely new. The Milky Way holds a uniquely important place in astronomy because it serves as a template, or reference model, for understanding countless other galaxies across the universe. Although we cannot observe our galaxy from the outside, the level of detail we can obtain from within is unmatched. We are able to measure the motions, compositions, ages, and distributions of individual stars, gas clouds, stellar clusters, and remnants with a precision that is impossible to achieve for distant galaxies. This makes the Milky Way the richest data set we have for studying how large spiral galaxies form, evolve, and interact with their environments. Many of the principles that astronomers apply to external galaxies, such as the structure of spiral arms, the role of dark matter in shaping rotation curves, the effects of star formation on surrounding gas, and the long-term consequences of galactic mergers, are first developed and tested using observations of the Milky Way. Because we can analyze stars and gas in 3 dimensions rather than relying solely on integrated light, the Milky Way becomes a kind of ground truth that informs theoretical models. These models can then be applied to interpret data from galaxies that are too distant or faint for such detailed study. Moreover, the Milky Way represents a typical massive barred spiral galaxy, one of the most common galaxy types in the universe. Understanding its disk, bulge, bar, halo, and satellite systems helps astronomers reconstruct the life cycles of similar galaxies. For example, by mapping stellar populations across our galaxy, we learn how spiral disks grow. By studying the halo's stellar streams, we uncover how galaxies assemble through mergers. By examining the chemical composition of stars, we trace the enrichment of the interstellar medium over billions of years. Every one of these insights provides a framework for interpreting observations of external galaxies. The Milky Way is also crucial for calibrating astronomical measurements. Distances to nearby stars allow us to refine methods for measuring distances to star clusters, Cepheid variables, supernovae, and eventually entire galaxies. These techniques underpin the cosmic distance ladder, the set of methods that enables us to estimate distances across the observable universe. In this sense, a proper understanding of the Milky Way affects not only galactic astronomy but cosmology itself. Finally, studying the Milky Way offers context for one of the most profound questions in science: how common life may be in the universe. By analyzing the distribution of planetary systems, the frequency of habitable zone stars, and the environments that affect planetary stability, we can estimate how typical or unusual our own system might be. As a result, the Milky Way is not just a scientific reference. It is a roadmap for understanding our place among billions of other galaxies, each containing billions of potential worlds. For all these reasons, the Milky Way remains one of the most important objects in the sky, a cosmic blueprint that allows us to explore not only its own history but the histories of galaxies throughout the universe. Studying the Milky Way is essential for understanding the process of star formation because our galaxy provides the closest and most detailed examples of every stage in the birth of stars. Unlike distant galaxies, where individual stars blend together into unresolved light, the Milky Way allows astronomers to observe star-forming regions one by one, from massive molecular clouds to newborn protostars and fully formed stellar clusters. This level of detail is crucial because star formation is a complex, multi-scale process governed by gravity, turbulence, magnetic fields, radiation pressure, and feedback from previous generations of stars. Only within our own galaxy can these factors be studied with the precision needed to build reliable physical models. The Milky Way contains a wide variety of environments where stars form, each offering unique insights. Giant molecular clouds such as Orion, Carina, Cygnus X, and Perseus reveal how cold, dense gas collapses into protostellar cores. Observations at infrared and submillimeter wavelengths allow astronomers to see through dust that obscures these regions in visible light, showing the birthplaces of stars as they begin to gather material. The ability to track individual protostars, measure their mass accretion rates, observe their jets and outflows, and map their surrounding disks gives researchers a direct view of how stars, and eventually planets, emerge from turbulent clouds of gas. The Milky Way also provides examples of feedback-driven star formation, where massive stars reshape their environments through powerful winds, ultraviolet radiation, and supernova explosions. These processes can either trigger new generations of stars by compressing nearby clouds or halt star formation by dispersing gas. Seeing both effects occurring simultaneously in different regions of our galaxy helps astronomers understand how stellar populations regulate the long-term evolution of galactic disks. Crucially, the Milky Way allows astronomers to link star formation to the large-scale structure of a spiral galaxy. By studying how star-forming regions align with spiral arms, density waves, and gas flows, scientists can determine how the overall morphology of the galaxy influences where stars are born. This connection between local physics and global structure is extremely difficult to observe in external galaxies, but becomes clear within our own. Furthermore, the Milky Way enables long-term studies of star formation across time. By examining clusters of different ages, from newborn to billions of years old, astronomers can reconstruct the galaxy's star formation history and compare it with theoretical predictions. This helps refine models of chemical evolution, gas recycling, and the life cycles of massive stellar populations. In short, the Milky Way is the most accessible and informative laboratory for studying star formation in the entire universe. It provides detailed, high-resolution examples of every physical mechanism involved in the transformation of interstellar gas into stars, allowing astronomers to build and test theories that can be applied to galaxies across cosmic time. The Milky Way is one of the most important laboratories in the universe for studying dark matter, because we can observe its gravitational effects on individual stars and gas clouds with far greater precision than in any external galaxy. Dark matter does not emit, absorb, or reflect light, making it invisible to all telescopes. Its presence must therefore be inferred from its influence on visible matter, and the Milky Way provides astronomers with an exceptionally detailed environment in which these gravitational signatures can be measured. By examining the motions of stars throughout the galaxy, especially in the disk, the bulge, and the extended halo, we can map how mass is distributed and determine where dark matter must be present to account for the observed dynamics. One of the clearest pieces of evidence comes from the Milky Way's rotation curve, which plots the orbital speeds of stars at different distances from the galactic center. According to Newtonian gravity, stars farther from the center should orbit more slowly, just as planets in the solar system do. Instead, the Milky Way's rotation curve remains almost perfectly flat. Stars tens of thousands of light-years from the center orbit just as fast as stars much closer in. This behavior is impossible to explain using only the visible mass of stars, gas, and dust. The only viable explanation is that the galaxy is embedded in a massive, roughly spherical halo of dark matter whose gravity provides the additional pull needed to maintain these high orbital velocities. Without dark matter, the outer parts of the galaxy would simply fly apart. Beyond the rotation curve, the Milky Way offers many other ways to detect dark matter's influence. Stellar streams, formed from the tidal disruption of dwarf galaxies and globular clusters, trace long, delicate arcs through the halo. Their shapes and motions are extremely sensitive to the underlying gravitational field. By mapping these streams with data from the Gaia mission, astronomers can detect clumps, distortions, or irregularities caused by dark matter substructures, small concentrations of dark matter that never formed visible stars. These observations provide evidence not just of dark matter's existence, but of its internal distribution and clumpiness, offering insight into its behavior on small cosmic scales. The Milky Way's satellite galaxies, such as the Large Magellanic Cloud, Sagittarius Dwarf, Sculptor, and Draco, also reveal important information. Many of these dwarfs are dominated by dark matter, and their orbital motions respond strongly to the halo's gravitational pull. By tracking how they move around the Milky Way, astronomers can estimate the total mass of the galaxy, most of which resides in the dark matter halo. Current estimates place the Milky Way's total mass at roughly 1 to 1.6 trillion solar masses, Yet only a small fraction of this mass is found in normal baryonic matter. The vast majority is dark matter, shaping the galaxy's structure and long-term evolution. Studying dark matter within the Milky Way is also critical for testing fundamental physics. The detailed behavior of stars in the inner regions, the heating of the stellar halo, and the finely mapped gravitational potential all place strong constraints on possible dark matter models, including cold dark matter, warm dark matter, and alternatives such as modified gravity. Because of the precision of local measurements, the Milky Way provides some of the most powerful tests of these theories in the entire universe. In essence, the Milky Way allows astronomers to probe dark matter with a level of accuracy unobtainable anywhere else. By studying how stars move, how streams warp, how satellites orbit, and how gas rotates, we can build a detailed map of the invisible mass that dominates our galaxy. This makes the Milky Way the cornerstone of dark matter research and a key to understanding one of the greatest mysteries in modern science. Understanding the Milky Way is essential for building accurate models of galactic evolution, because it is the only large spiral galaxy we can observe from the inside with extremely high precision. Every stage of a galaxy's life, its birth, growth, interactions, and long-term transformation, is encoded in the structures, motions, and chemical compositions of the stars that fill the Milky Way. By studying these components in detail, astronomers can reconstruct the processes that shaped our galaxy and apply those lessons to interpret galaxies across the universe. The Milky Way's stellar populations offer a direct timeline of its past. Older stars in the halo and thick disk show low metallicity, reflecting conditions in the early universe when heavy elements were scarce. Younger stars in the thin disk contain progressively higher amounts of metals, indicating ongoing cycles of star formation, supernova enrichment, and gas recycling. Mapping these metallicity gradients allows scientists to understand how gas flowed into the galaxy, how the disk grew over billions of years, and how different generations of stars contributed to chemical evolution. In combination with precise stellar ages provided by missions like Gaia, the Milky Way acts as a living archive of galactic history. Dynamical structures also reveal key evolutionary processes. The bar in the galactic center channels gas inward, driving waves of star formation and shaping the galaxy's spiral pattern. The spiral arms themselves behave as density waves that compress gas clouds, triggering new generations of stars. By observing how gas and stars respond to these large-scale patterns today, astronomers can model how similar structures form and dissolve over cosmic time. The distribution of angular momentum in the disk, the presence of resonances caused by the bar, and the thickness variations in the stellar layers all help refine simulations of how spiral galaxies stabilize and evolve. Equally important are the remnants of past mergers. The Milky Way bears unmistakable scars of ancient collisions, such as the Gaia-Enceladus merger and the ongoing disruption of the Sagittarius dwarf galaxy. These events dramatically rearranged the galaxy's structure, heating the disk, populating the halo, and altering rotational dynamics. By studying the motions and chemical signatures of stars left behind by these mergers, scientists can reconstruct the sequence of past interactions. These observations provide critical calibration for cosmological simulations, which predict that large galaxies grow through repeated mergers, confirming that the Milky Way follows the same evolutionary pathways as other major spirals. Even the dark matter halo contributes essential information. Its shape, extent, and substructure all influence how gas settles into the disk, how satellite galaxies orbit, and how the Milky Way interacts with its cosmic environment. By measuring these features through stellar motions and gravitational effects, astronomers can refine models of how galaxies acquire mass and how their halos evolve over billions of years. Together, these observations make the Milky Way a benchmark for understanding galactic evolution in general. It provides the highest resolution data on star formation, chemical enrichment, mergers, disk dynamics, and dark matter structure. By comparing simulations to the detailed reality of our galaxy, scientists can test which physical processes dominate at different stages of galactic growth. In this way, the Milky Way becomes both a case study and a template, allowing astronomers to model how typical spiral galaxies form, change, interact, and ultimately transform over cosmic time. We live inside a vast and ancient city of stars, a place so immense that even our imagination struggles to grasp its true scale. Every night, when the sky grows dark and quiet, the Milky Way arches above us like a glowing river, an echo of billions of suns woven together across unimaginable distances. From the inside, it feels familiar, almost gentle, like a soft band of light guiding us through the darkness. But in reality, we are drifting through a cosmic metropolis larger than anything the human mind was ever meant to comprehend. This galaxy is not just a backdrop to our lives. It is the cradle of everything we are. Every atom of our bodies, every breath we take, every dream we carry was forged in the furnaces of its long-dead stars. We are children of this place in the most literal sense, made of its dust, held by its gravity, illuminated by its light. To study the Milky Way is to read the autobiography of our own existence, written in starlight, in nebulae, in ancient orbits that long predate the Earth itself. And when we look outward, beyond our small blue planet, we find ourselves surrounded by a silent infinity. Trillions of other galaxies swirl in the darkness, each with its own worlds, its own histories, its own possibilities. Yet this single spiral shaped by time, chaos, and stardust, is the one that shelters us. It is our home even when we forget it, even when we take the night sky for granted. In its arms we travel, generation after generation, never noticing the subtle motion that carries us around the galactic center once every 200 million years. We are part of a journey so long that no human language has words for its duration. And still, the galaxy turns, patient and ancient, unconcerned with the brevity of our stories. Understanding the Milky Way is not just a scientific pursuit. It is an act of remembering where we come from. It reminds us that we are more than individuals living brief lives on a small world. We are fragments of a cosmic story billions of years in the making. When we explore our galaxy, we explore ourselves, our origins, our place in the universe, and the fragile beauty of our existence. The Milky Way is not just a galaxy. It is our cosmic home. A luminous reminder that, in a universe filled with darkness, we are made of light. Because we live inside the Milky Way, we cannot step outside it and look back. Instead, astronomers rely on indirect methods, and among the most powerful are radio observations, a way to see through dust and map structures hidden from optical telescopes. The backbone of this approach is the 21-centimeter hydrogen line, a specific wavelength of radio emission produced when the electron in a hydrogen atom flips its spin relative to the proton. This tiny quantum transition is extraordinarily useful. Neutral hydrogen, Hi, fills the Milky Way's disk and spiral arms, and radio waves at 21 centimeters can pass through interstellar dust without being blocked. By tuning radio telescopes to this wavelength, astronomers can detect hydrogen across enormous distances and create large-scale maps of the galactic plane. Even more importantly, the 21 centimeters line carries Doppler information. As hydrogen clouds orbit the galactic center, their motion shifts the wavelength of the emitted radio waves slightly toward the red or blue end of the spectrum, depending on whether they are moving away from or toward us. By measuring these shifts across the entire sky, astronomers can reconstruct the rotation curve of the galaxy, the speed of gas at different distances from the center, and trace the locations of the spiral arms that cannot be seen directly from Earth. This technique is how scientists discovered the Milky Way's spiral structure in the mid-20th century, and how they continue refining it today. Arrays like the Very Large Array, VLA, Arecibo's legacy data, and modern surveys such as Hi4Pi allow researchers to piece together a detailed, three-dimensional map of hydrogen gas. Through these observations, we can identify the position, thickness, and motion of the spiral arms, locate massive gas complexes, and understand how the galaxy rotates as a whole. Radio astronomy turns the invisible into the visible. It lets us see through the dust, measure the heartbeat of the Milky Way, and trace the skeleton of hydrogen that shapes the structure of our cosmic home. Infrared telescopes have transformed our ability to study the Milky Way because they reveal a galaxy that is normally hidden behind thick curtains of interstellar dust. Dust grains absorb and block visible light, especially in the densest regions of the disk and spiral arms, but infrared radiation passes through these dusty layers with far less obstruction. As a result, telescopes such as Spitzer and WISE give us a clearer, deeper, almost X-ray-like view into the structure of our own galaxy, exposing stars, clusters, and gas formations that optical instruments cannot detect. The Spitzer Space Telescope, operating from 2003 to 2020, produced some of the most detailed infrared maps of the Milky Way ever made. It revealed the true architecture of the galactic disk, long arcs of dust, branching filaments, and the precise shape of the central bar. Spitzer's sensitivity allowed astronomers to detect millions of stars across the plane of the galaxy, including young stellar objects still embedded in their natal clouds. Because infrared wavelengths highlight warm dust heated by massive stars, Spitzer also traced the pillars, ridges, and cavities sculpted by radiation, revealing the stitching of the Milky Way's internal structure. Meanwhile, WISE, the Wide-Field Infrared Survey Explorer, conducted a full-sky infrared survey, mapping the entire Milky Way at multiple infrared wavelengths. Its data uncovered thousands of new star clusters, traced the thickness of the disk, and identified the locations of long, narrow structures such as infrared dark clouds, the coldest, densest regions where future stars form. WISE also highlighted the detailed pattern of columns, lanes, and filaments of dust that weave through the spiral arms like the framework of a colossal cosmic web. Together, these infrared observatories give us a structural blueprint of the Milky Way. They reveal where stars are born, how dust flows along the spiral arms, how the bar channels material inward, and how the disk's hidden layers overlap. Without infrared telescopes, our view of the Milky Way would be like trying to understand a forest by looking only at its shadows. With them, we see the texture, depth, and true form of our galaxy's luminous architecture. The Gaia Space Telescope has transformed our understanding of the Milky Way more profoundly than any mission before it. Launched by the European Space Agency, Gaia is designed to do one thing better than any instrument in history: measure the positions, motions, and distances of stars with extraordinary precision. Instead of producing stunning images, Gaia produces something far more valuable: a complete, three-dimensional map of our galaxy, built star by star. Gaia observes the sky repeatedly over many years, measuring tiny shifts in the positions of stars caused by Earth's orbit around the Sun. These shifts, parallaxes, allow astronomers to determine stellar distances with accuracy that was previously unimaginable. In addition, Gaia tracks proper motions, the sideways drift of stars across the sky, and measures their radial velocities, which reveal how fast stars move toward or away from us. The result is a catalog containing over 1.8 billion stars, each with precise coordinates and motion vectors. This data set has revolutionized our ability to reconstruct the Milky Way's structure. For the first time, we can map the real shape of the spiral arms, trace the thickness and warp of the galactic disk, and identify previously hidden streams of stars formed by ancient collisions with dwarf galaxies. Gaia has revealed waves and ripples moving through the disk, signatures of past gravitational disturbances, and even remnants of a massive merger event known as the Gaia-Enceladus collision, an ancient galaxy whose stars now orbit within our halo. Gaia's precision also allows astronomers to calculate the orbits of stars far into the future and deep into the past, reconstructing the history of the Milky Way as if it were a living documentary. The mission has rewritten our understanding of how the galaxy formed, how it evolves, how it interacts with satellite galaxies, and how structures like the bar, disk, and halo change over time. In short, Gaia has not just improved our map of the Milky Way, it has given us an entirely new one. With its data, astronomers no longer rely on indirect approximations but can study the galaxy as a dynamic, three-dimensional system. Gaia has turned the Milky Way from a distant abstraction into a measurable, evolving structure. X-ray astronomy allows us to uncover the most extreme, energetic, and violent environments in the Milky Way, regions completely invisible in optical or even infrared light. High-energy radiation in the X-ray band is produced only by processes involving intense heat, strong magnetic fields, or extreme gravity. This makes X-ray telescopes indispensable for detecting neutron stars, stellar mass black holes, supernova remnants, and the diffuse hot gas that fills parts of the galactic halo. In the Milky Way, many neutron stars and black holes do not emit visible light, but they reveal themselves when they pull matter from a companion star. As gas spirals into these compact objects, it forms an accretion disk heated to millions of degrees, producing bright, unmistakable X-ray emission. Observatories such as Chandra, XMM Newton, and NU Star have catalogued thousands of these sources, allowing astronomers to study how compact objects evolve, how binary systems transfer mass, and how stellar remnants influence their surroundings. X-ray observations also reveal supernova remnants, where shock waves from exploded stars heat surrounding gas to tens of millions of degrees. These remnants glow in intricate X-ray structures, shells, filaments, and hot plasma clouds. They are crucial for understanding how heavy elements are dispersed through the galaxy and how supernova shocks trigger new bursts of star formation. Beyond individual objects, X-ray telescopes map the Milky Way's hot interstellar medium, a diffuse, million-degree gas that permeates regions above and below the disk. This hot gas, detected only in X-rays, provides clues about large-scale outflows from the galactic center, including possible ancient eruptions from the supermassive black hole Sagittarius A star. It also helps trace the structure of the halo and the interactions between the Milky Way and its satellite galaxies. In essence, X-ray astronomy reveals the Milky Way's hidden skeleton of high-energy processes. It exposes objects and phenomena that cannot be seen by any other means, allowing scientists to probe extreme physics, compact objects, and the turbulent hot gas that shapes the galaxy on vast scales. The Milky Way's rotation is one of the clearest windows into the invisible structure that holds our galaxy together. When astronomers measure how stars and gas orbit the galactic center, they can construct a rotation curve, a graph comparing orbital speed to distance from the core. If the galaxy were made only of the matter we can see, stars, gas, and dust, the rotation curve would fall sharply beyond the inner regions, just as planets move more slowly the farther they orbit from the sun. But observations show something radically different. The rotation curve remains flat. Stars tens of thousands of light-years from the center orbit just as fast as those much closer in, defying the expectations of Newtonian gravity if only visible matter were present. This means the outer galaxy is moving far too quickly to be held together by the luminous mass we observe. Without an additional gravitational component, the Milky Way would fly apart. The only explanation consistent with the data is the presence of a vast, unseen halo of dark matter, a form of matter that interacts through gravity but not through light. Dark matter contributes the overwhelming majority of the Milky Way's mass, forming a massive, roughly spherical halo that extends far beyond the visible disk. The rotation curve is, therefore, not just a measurement of stellar motion, it is one of the strongest empirical proofs that dark matter must exist. Through radio observations of hydrogen gas, optical spectroscopy of stars, and modern surveys like Gaia, astronomers have refined the rotation curve to extraordinary precision. No matter how it is measured, the result is the same. The Milky Way rotates as if it is embedded in a colossal gravitational framework that cannot be explained by baryonic matter alone. This dynamic behavior reveals that the Milky Way is not simply a collection of stars orbiting a luminous center. It is a dark matter-dominated system whose shape, stability, and evolution are governed by a hidden structure we can measure only through its gravitational effects. The flat rotation curve remains one of the most important and direct pieces of evidence for dark matter in the universe. The spiral arms of the Milky Way are not rigid structures made of fixed stars. Instead, they behave like gravitational waves of density that ripple through the galactic disk. This concept, known as density wave theory, explains why spiral arms maintain their shape over billions of years, even though the stars within them move at different orbital speeds. If the arms were solid formations, they would quickly wind up and disappear. But because they are waves, not material objects, they can persist much longer. As the density wave travels through the disk, it acts like a traffic jam on a cosmic scale. Stars, gas, and dust move into the region of higher density, slow slightly, compress together, and then flow out the other side. This temporary compression is enough to trigger star formation. Molecular clouds collapse under the increased pressure, leading to the birth of bright, massive stars. These hot blue stars illuminate the spiral arms, making them appear more prominent even though the stars themselves soon move onward. These waves do not only shape the spiral arms, they also create subtle gravitational oscillations throughout the disk. Surveys such as Gaia have revealed that the Milky Way's disk is not perfectly flat but exhibits vertical ripples, bends, and warps, likely caused by density waves interacting with past mergers, satellite galaxies, or the influence of the galactic bar. These waves can reorganize gas flows, shift the positions of spiral features, and even affect the long-term evolution of the disk structure. In essence, the Milky Way's spiral arms are living, moving patterns, sculpted by gravity and reinforced by the constant interplay of stars and gas. They are not sculpted once and frozen in time. They are continuously regenerated by density waves, making them dynamic signatures of the galaxy's internal motion and gravitational rhythms. The Milky Way's disk is not a flat, rigid structure. It moves, bends, and oscillates like a vast sheet of cosmic water. For decades, astronomers suspected that the galaxy might be slightly warped, but only with the arrival of Gaia did the full picture become clear. Gaia's precise measurements of billions of stars revealed that the disk is undergoing large-scale vertical waves, rising and falling by thousands of light-years in different regions. These motions are not random. They form coherent, galaxy-wide patterns, as if an enormous ripple were passing through the disk. This galactic wave manifests in several ways. Stars in some regions sit noticeably above the average plane of the galaxy, while stars in other regions lie below it. Their velocities also show a rhythmic pattern, large groups of stars moving upward or downward together. When scientists map these motions in 3 dimensions, they see a vast, undulating structure extending across tens of thousands of light-years. The Milky Way, in a literal sense, is vibrating. What causes this? The leading explanations point to gravitational disturbances. One possibility is a past encounter with a dwarf galaxy, perhaps the Sagittarius dwarf galaxy, which plunged through the Milky Way multiple times over billions of years. Each passage would have sent gravitational shocks through the disk, much like a stone dropped into water. Another possibility is the influence of the dark matter halo itself. If the halo is not perfectly smooth, its clumps could tug on the disk, causing long-lived oscillations. Density waves from spiral structure and interactions with the central bar may also contribute. Gaia has shown that these ripples are not isolated features, but a widespread, dynamic behavior built into the Milky Way's structure. The galaxy is still responding to ancient collisions, still vibrating from gravitational echoes millions of years old. These oscillations influence star orbits, the distribution of gas, and even the pattern of spiral arms. The picture that emerges is of a galaxy alive with motion, not a quiet, stable disk, but a resonant, shifting system shaped by its past and constantly evolving. One of the most dramatic events in the Milky Way's early history was the ancient merger with a dwarf galaxy now known as Gaia Enceladus, or the Gaia Sausage. This collision, which occurred roughly 8 to 10 billion years ago, profoundly reshaped the structure of our galaxy and left behind unmistakable signatures that astronomers only recently uncovered through Gaia's precise stellar data. Before the merger, the Milky Way was a much smaller, more primitive system. When Gaia Enceladus collided with it, the encounter was not a gentle incorporation. It was a violent, high-energy impact between 2 sizable galaxies. The gravitational shock from the collision stirred the Milky Way's early disk, heating and scattering many of its stars into elongated, eccentric orbits that now populate the inner halo. The stars from Gaia Enceladus itself were also flung into extended, sausage-shaped trajectories, giving rise to the nickname Gaia Sausage structure. These stars can still be identified today by their unique characteristics. They follow highly radial orbits, stretching far from the galactic center before plunging back in, unlike the more circular orbits of native Milky Way stars. They are also old and relatively metal-poor, showing that they were born in a smaller, less chemically evolved galaxy. Gaia's data revealed millions of such stars across the sky, forming vast streams and clumps that trace the remnants of the long-disrupted dwarf galaxy. This merger did more than simply leave debris. It fundamentally changed the Milky Way's shape and mass distribution. Many astronomers believe that the early thick disk of our galaxy was created or heavily altered by this impact. The merger also contributed significantly to the mass of the halo and added countless stars and globular clusters to our galaxy's population. In effect, Gaia Enceladus helped transform the Milky Way from a young, growing system into the massive spiral galaxy we recognize today. The discovery of Gaia Enceladus is one of the most important breakthroughs in modern galactic archaeology. It shows that even billions of years later, the Milky Way still carries the fossilized scars of ancient collisions, encoded in the motions and chemistry of its stars. Through Gaia's measurements, we can now reconstruct this long-lost galaxy and understand its pivotal role in shaping our cosmic home. Another unmistakable relic of the Milky Way's dynamic past and present is the ongoing tidal destruction of the Sagittarius dwarf spheroidal galaxy, SGR-DSPH. Unlike the ancient Gaia-Enceladus merger, which occurred billions of years ago, this interaction is happening right now, unfolding across the sky as a dramatic example of how the Milky Way continually reshapes the smaller galaxies orbiting it. The Sagittarius dwarf galaxy was discovered in 1994, astonishing astronomers because it lies extremely close to the center of the Milky Way, much closer than any major companion should be if it had remained intact. Its position immediately revealed that this galaxy is not in a stable orbit. Instead, it is being pulled apart by the Milky Way's gravitational field. SGR-DSPH was once a compact, elliptical galaxy containing hundreds of millions of stars. But repeated close passages through the Milky Way's disk and halo have stripped away huge amounts of its material, stretching it into a spectacular stellar tidal stream that now wraps around our galaxy multiple times. This stream is one of the most extensive known structures in the sky. As the Milky Way's gravity tears stars from Sagittarius, they are pulled into long, looping arcs that encircle the galaxy like ribbons. These arcs contain ancient stars that retain the chemical fingerprints of Sagittarius itself, low metallicities, characteristic abundance ratios, and distinct motions that allow astronomers to identify them as extragalactic in origin. Observations from surveys such as SDSS-2 MASS, and especially Gaia show that the stream forms a vast, coherent structure, tracing a three-dimensional orbit of debris around the Milky Way. The interaction has been so strong that Sagittarius has passed through the Milky Way's disk at least 3 times, each time punching through like a stone through water. These passages may have created ripples and waves in the Milky Way's disk, features we now observe in Gaia data as vertical oscillations and warps. Some researchers suggest that Sagittarius' repeated impacts may have even influenced episodes of star formation in the Milky Way by disturbing gas clouds and triggering compression. What remains of the Sagittarius galaxy today is only a faint core, barely holding together. The rest of it, billions of solar masses of stars, is already integrated or in the process of being integrated into the Milky Way's halo. In a sense, the Sagittarius dwarf galaxy is a living demonstration of galactic cannibalism, the slow but inevitable process by which large galaxies grow by absorbing their smaller neighbors. The ongoing dissolution of Sagittarius provides astrophysicists with an invaluable natural laboratory. By mapping its streams, astronomers can reconstruct the Milky Way's gravitational potential and better understand the distribution of dark matter in the halo. The shape, curvature, and density of the stream act like test particles, tracing the invisible mass around our galaxy. And because Sagittarius is still being torn apart today, its stellar stream offers a real-time glimpse into the active evolution of the Milky Way. The Sagittarius dwarf galaxy is therefore not merely a footnote in our galaxy's history. It is a vivid reminder that the Milky Way is not static, but a dynamic system continually shaped by the galaxies that fall into it. Every star torn from Sagittarius and sent sweeping across the sky carries a piece of that story, forming one of the most beautiful and scientifically rich structures in the local universe. High above and far below the bright, star-filled disk of the Milky Way lies a vast, ghostly region known as the galactic halo, an enormous, dim sphere of space that extends for hundreds of thousands of light years. To the casual observer, it appears empty. But to astronomers, the halo is a living archive of cosmic catastrophes, holding the preserved remains of every major galactic collision that shaped the Milky Way over billions of years. It is here, in the halo's quiet darkness, that the galaxy stores the long, fading memories of its violent past. The halo contains stars so old that many of them formed before the Milky Way had even settled into its familiar spiral shape. But what makes the halo extraordinary are the stellar streams, long, delicate rivers of stars stretched across the sky. These streams are the remains of dwarf galaxies and globular clusters that ventured too close to the Milky Way and were torn apart by its gravitational forces. Their stars were pulled out and scattered along orbital paths, forming what look like glowing arcs or serpentine streaks wrapped around the galaxy. Each stream is a fossil of a destroyed world. For example, the Sagittarius stream, the Helmer stream, the GD1 stream, the Orphan stream, and others all trace the paths of ancient catastrophes. Galaxies shredded, clusters dissolved, their stars left drifting as a permanent reminder of the Milky Way's endless hunger. The halo is threaded with these structures, some stretching tens of thousands of light years, each containing stars with unique chemical signatures that reveal their origin. These chemical fingerprints allow astronomers to identify which disrupted body each stream once belonged to, almost like reconstructing the genealogy of galaxies. In addition to narrow, well-defined streams, the halo also contains vast, faint arcs and diffuse shells of stars, enormous, fog-like structures that are the remnants of the largest mergers. These enormous arcs form when a dwarf galaxy is swallowed in a single dramatic event, dispersing its stars in great looping waves that take eons to fade. Gaia's precise measurements have revealed several such enormous debris fields, including the remnants of the Gaia-Enceladus merger, which left a thick population of stars with characteristic motions and low metallicities scattered throughout the halo. Together, these streams, arcs, and debris clouds transform the halo into a kind of three-dimensional map of the Milky Way's past collisions. By studying their motions, shapes, and chemical compositions, astronomers can reconstruct when each event occurred, how massive the incoming galaxy was, and how the Milky Way changed as a result. These structures behave like cosmic seismographs, recording the gravitational ripples produced by each catastrophic encounter. The halo also serves as one of the best places to study dark matter, because the orbits of its streams reveal the shape and mass distribution of the invisible halo that surrounds the Milky Way. The way these stellar rivers stretch, twist, and bend is controlled by the underlying dark matter potential, meaning the halo's debris is not only an archive of past catastrophes, but also a tool for uncovering the universe's most elusive substance. In the end, the Milky Way's halo is not an empty void but a historical library written in starlight, a sprawling, silent record of every galaxy the Milky Way has devoured. Each stream, each arc, each faint ribbon of stars is a page in that story, tracing the ancient collisions that built the galaxy we now call home. Surrounding the Milky Way is a small empire of faint, fragile dwarf galaxies, remnants of the early universe and survivors of billions of years spent orbiting a much larger host. These dwarf companions are among the most ancient stellar populations we can observe, and each one offers a different window into the formation and evolution of galaxies. Though they appear small and dim compared to the Milky Way, their histories are just as rich, and their interactions have shaped the structure of our galaxy in profound ways. The most prominent and easily visible members of this family are the Large Magellanic Cloud, LMC, and the Small Magellanic Cloud, SMC. These two irregular dwarf galaxies are among the closest galaxies to the Milky Way, and can be seen with the naked eye from the southern hemisphere. The LMC is the more massive of the two, containing vibrant star-forming regions, such as the Tarantula Nebula, one of the most active stellar nurseries in the local group. Its gravitational dance with the SMC has created long tidal bridges and streams of gas, including the Magellanic Stream, which trails behind them as they orbit the Milky Way. The SMC, though smaller, is similarly rich in gas and young stars, and the gravitational interaction between the clouds continues to shape both of their structures. Another key satellite is the Sagittarius dwarf spheroidal galaxy, which is currently in the process of being disrupted by the Milky Way's gravitational field. Sagittarius has already passed through the Milky Way's disk multiple times, leaving behind a vast stellar stream that wraps around the entire galaxy like a pale ribbon. Much of its original mass has been stripped away, and its stars now form one of the most dramatic tidal features in our halo. This ongoing interaction provides astronomers with a unique laboratory for studying galaxy cannibalism in real time. The Fornax dwarf galaxy is one of the more massive and luminous spheroidal satellites. Fornax is remarkable because it hosts a collection of its own globular clusters, which is unusual for such a small galaxy. These clusters give astronomers insight into early star formation episodes and the chemical evolution of dwarf galaxies. Despite being faint and diffuse, Fornax contains stars spanning a wide range of ages, suggesting a complex history of intermittent star formation before environmental effects from the Milky Way quenched further growth. The Milky Way also hosts several extremely faint dwarf spheroidal galaxies, such as Leo I and Leo II. Leo I is especially intriguing because of its high velocity. It is moving fast enough that astronomers once debated whether it might escape the Milky Way's gravitational pull. Both galaxies are dominated by very old, metal-poor stars, and their structures are so diffuse that they are barely distinguishable from the background sky. Their chemical makeup helps researchers reconstruct the sequence of events that shaped the early Milky Way. Finally, there are ultrafaint dwarfs like Draco and Ursa Minor, which are among the most dark matter-dominated objects in the universe. These galaxies contain only a few tens of thousands of stars, yet their internal motions reveal enormous dark matter halos. The stars within Draco and Ursa Minor formed long ago and have changed little since, making them pristine relics of the early universe. Their extreme faintness and simplicity make them valuable probes of dark matter and primordial star formation. Together, these dwarf galaxies form a complex and dynamic system orbiting the Milky Way. Their motions, tidal interactions, and chemical fingerprints help astronomers reconstruct the Milky Way's growth over billions of years. Some satellites are in the process of being consumed. Others remain stable in long, looping orbits. Still others may yet be undiscovered, hidden in the faint outskirts of the halo. Studying these companions allows scientists to understand not just our own galaxy's history, but the fundamental processes that shape galaxies throughout the universe. The Large Magellanic Cloud, LMC, is not just the brightest and most massive satellite galaxy orbiting the Milky Way, it is also one of the most influential. Its gravitational presence is so substantial that it is actively reshaping the structure of our galaxy's dark matter halo, stirring both visible and invisible components as it moves through space. Far from being a passive companion, the LMC is a dynamic intruder whose arrival has triggered a profound response across the Milky Way's outer regions. The LMC contains roughly 10 to 20 billion solar masses in stars and an even larger reservoir of gas, but its most significant contribution is its dark matter halo, which may reach 100 to 250 billion solar masses, making it comparable in mass to a small galaxy cluster. Because of this, the LMC does not simply orbit the Milky Way like a lightweight satellite. Instead, it creates a gravitational wake within the Milky Way's dark matter halo as it moves, dragging material behind it and causing the halo to shift its center of mass. Recent Gaia data and simulations show that the Milky Way itself is being pulled several thousand light-years toward the LMC, demonstrating that the LMC is massive enough to alter the motion of our own galaxy. This gravitational wake has been detected indirectly through the motions of halo stars, which show subtle patterns, swirls, and asymmetries consistent with the LMC's influence. These distortions reveal that the Milky Way is not in perfect dynamical equilibrium. Instead, it is being disturbed by the infall of this massive satellite. The LMC's passage is reshaping the density of dark matter in the outer halo, creating a lopsided distribution that future measurements may be able to map in detail. As for the future, current models suggest that the LMC is not in a stable, repeating orbit. Instead, it is on a decaying trajectory, gradually losing orbital energy due to dynamical friction, the drag caused by the gravitational interactions between the LMC and the Milky Way's dark matter halo. Over the next 1 to 2 billion years, this friction will likely cause the LMC to spiral inward toward the Milky Way's center. When that happens, the LMC will almost certainly be fully absorbed by the Milky Way. This merger will not be as large as the future Andromeda-O-Milky Way collision, but it will still be a significant event. The LMC's stars will be stretched into long streams, its gas may ignite new waves of star formation, and its dark matter will merge into the Milky Way's halo, increasing the overall mass of the galaxy. Some simulations predict that the infall of the LMC could trigger a mild starburst in the Milky Way's disk, or subtly reconfigure the spiral structure. The central bar may lengthen, the halo may become more massive and more asymmetric, and the outer disk may be perturbed. The merging process will be slow and drawn out, but its effects will persist for billions of years. In essence, the LMC is not just orbiting the Milky Way, it is on a slow, inevitable journey toward becoming part of it. Today we witness only the early stages of this transformation. The gravitational wake, the shifting halo, and the disturbed motions of stars reveal the beginning of a cosmic story that will eventually conclude with the Milky Way consuming one of its largest companions.